In this paper, we propose a novel framework to simulate multi-domain subspace deformation in real time with corotational elasticity. The deformable object is decomposed into several subregions called domains, and we construct the subspace at each domain instead of the entire deformable body. The deformation subspace is constructed with a novel boundary-driven approach. We generalize the boundary displacement geometrically and minimize the system's potential energy within the boundary constraint. This can be done by solving the static equilibrium. The rigid boundary modes take advantage of the linearity of infinitesimal rigid body motion and construct the corresponding linear subspace with small size. We also use the manifold harmonic spaces as complementary soft boundary modes when the interface is big and the deformation is large. The domain coupling becomes trivial and can be achieved by the Lagrange multiplier method. On top of boundary modes, inertia modes are also included in the system in order to capture the vibration induced by accelerated body motion. The large deformation is handled with per-node corotational elasticity with model reduction. In this comparison, we quantitatively compare the simulation accuracy of our method with other simulators. From right to left, each bar model is simulated with nonlinear full-space simulator, modal derivative, deformation substructuring, modal warping, and our method with only rigid boundary modes and with soft boundary mode. All the simulators use the same material settings. The figure shows the average y directional displacement of the vertices on the free end of the bar model. We can see that all the simulators have very similar trajectories. We compare the result of our method and the method using nonlinear multi-domain subspace with penalty force. With a small number of modes, cracks are visible between domains with penalty force, and they disappear with increased number of subspace modes, while our method guarantees seamless domain coupling even with a small number of subspace spaces. Next, we compare our method with deformation substructuring using rigid interface fitting. The Tyrannosaurus model is decomposed into 17 domains over about 120,000 tetrahedral elements. We see that for large deformation in interface, pure rigid boundary fitting will also induce domain cracks. In addition, due to the interface lumping, the deformation sequence is also slightly different. Our method avoids boundary locking and overconstraint. Domains are exactly coupled without any artifacts, and plausible result is produced. Our method is able to handle large deformations well. The sunflower model consists of about 47,000 elements with 13 domains. Leaves are assigned with higher order inertia modes and softer material. Our framework also supports direct user manipulation. The fish model consists of 110,000 elements with 10 domains and it is manipulated in real time by the user. Two interfaces are also constrained with interactively specified rotation, and natural deformation is simulated. Finally, we show a seaboat model with over 250,000 elements with 7 loops. It can also be interactively manipulated by the user. We applied scripted force at the mast and wind field at the canvas. We assign highly stiff material to the mast and soft material to the canvas, while higher order inertia modes are also assigned to the canvas for enriched local deformation. Interesting results can be simulated. Thank you.